Now, one important concept which I would like to refresh, clarify is the comparison between the intercept method and the long bike run method. Now, I told you that wherever we use the longitude by chronometer method, it is possible to use the intercept method also. Now, it should be clear in your mind that whichever method you use, whether you use long bicron or you use intercept, in both the cases, the position line what you are going to obtain will be the same. There will be no difference between the position line. It will be the same because of a concept. The concept is that from a single celestial body at a particular time, irrespective of whichever method we use, we can obtain only one single position line. So from a single celestial body at any particular time, we can obtain only a single PL. If we want two position lines, two different position lines, either we have to use two different bodies, or if we are not having any other body, let us say during daytime, we don't have any other body. At the time of twilight, we have a lot of stars which are available to us. So you can pick up two different bodies to get two PLs. Why we are interested in two PLs? Because two PLs are required to fix the vessel's position. A single PL is not going to fix the vessel's position. So in twilight, a lot of stars are available. We have access to many celestial bodies. But during daytime, it is possible only the sun may be there. Now, in that case, if we have only one single celestial body and you want to obtain two PLs, the only option is to stagger the observation. You take one observation at a particular time, wait for some time for the body to move, and then after some time you take another observation. That is known as a staggered observation, and you will get two different PLs. But at a single time from a single body, we can obtain only a single PL, irrespective of the method which we use. Now, how is that possible? We had different formula for intercept and for long bicron. How both of them can give us the same PL? Let's try to understand using this diagram. Now, this horizontal line which you see is the DR latitude, labeled here as DR lat. This vertical line which I'm highlighting right now with the laser pointer is the DR longitude. And the delta position which you see here is the DR position. Now there is one more longitude which is given here, highlighted by the laser pointer now. This is the observed longitude. Let's assume we solved a particular question and this is the observed longitude what we obtained. Now using the long bicron method, we know that the PL is going to pass from DR lat and observe long, that is point Bravo. So we draw the azimuth of the body. This is the azimuth of the body. And perpendicular to the azimuth, the solid black line with arrows on both the sides, you have the position line. So this was using the long bicron method. Now, if the duty officer had used the intercept method in this particular case, what would have happened is, now for intercept method, the reference position is the DR position. So we will have to start from position D, delta. Now from this delta position, you will have to first plot the intercept. In this case, the intercept is away. So you have the azimuth of the body plotted here. The intercept is away. So you go from the DR position away from the body. The body is in this side. So you go away from the body a distance equal to the intercept, and the ITP which you are going to get will be this point Papa. And this ITP will lie exactly on the long bichrome PL. So from this ITP, if you draw a line perpendicular to the azimuth of the body, you will get the PL again. And you will observe that from both these methods, whether it is long bichrome or the intercept method, the position line obtained will always be same. We cannot have two position lines from a single body at a single time by using two different methods, intercept and long bichrome. That's not possible. So this is the concept or comparison of longitude by chronometer and the intercept method. Any doubts in this, Pita? Is that clear?
Clear.
Very good, Pita. Great. Let's move on to our next method now, which is X meridian. Now, first of all, the meaning of this method, X basically means close. So X meridian basically means that the body is close to the meridian. It could be east of the meridian or west of the meridian, but it is close to the meridian. Now, practically, this X meridian method is not used nowadays. It has almost lost its practical relevance because we have other methods which are available which can be utilized in place of X meridian, like intercept. Intercept can be used in these situations where X meridian is used, and it does not have any restrictions also. X meridian method has some restrictions. It can be only used for a particular amount of time or for a period of time. So we have the better method available to us now, and nowadays we use that. But theoretically, yes, sometimes questions based on X meridian they drop in the papers. So we should be familiar with the working out of the X meridian site. Let's now go into the method. I will also explain to you the relevance, practical relevance of X meridian, how it is practically actually taken on board, and its comparison to intercept. So for that, let's first understand the procedure of how X meridian method is solved. Let's see the information which is provided to us in the question. They will provide us the date and time. The time could be GMT or chronometer. In case of chronometer, there could be a 12-hour ambiguity, which will be resolved using the AM/PM indication given in the question. The second set of information is they will tell us that the body is close to the meridian or the body is near the meridian. Along with it, we will have the sextant altitude of the body, and as usual, the index error, the error of the instrument, the sextant, and the height of eye provided to us for dip correction. And we will also have the DR position given in these questions. This is the information which is provided. Almost similar to what was there in long bichrome or intercept, with only one addition, that a indication is given that the body is close to the meridian or near the meridian. Now, as far as our exam questions are concerned, wherever this indication is given, body is close to the meridian or near the meridian, the paper setter wants you to attempt this question using the X meridian method. So this is the intimation provided to us to denote that X meridian is to be used in these questions. So let's go into the procedure now. The first step is similar to what we have already done. We obtain the almanac information of the body. We get the hourly GHA, apply the increment, apply the V correction increment if required in case of planets and moon, and we get the accurate GHA of the body. We have the DR longitude available to us, and once applied to the accurate GHA, we get the LHA of the body, and this LHA gives us angle P. Now we obtain the hourly declination from the day page. We get the value of hourly declination. We check its increment from the increment table, apply it, and that gives us the correct declination, the accurate declination of the body. So this is the first step. Now in the second step, we correct the altitude of the body. The sextant altitude, we apply the index error. If it is on, it is put off, that means negative. If it is off, it is put on, that means positive. Then we apply the dip correction from the height of I, which is provided to us in the questions. And once these two are applied, we get the apparent altitude of the body. Now to this apparent altitude, we apply the total correction, and this gives us the true altitude of the body. Once true altitude is obtained, we can get the true zenith distance of the body, which is 90 minus true altitude. So once you have calculated up to here, you are ready to go into the intercept formula. Let's see the intercept formula. Intercept formula is cos of mzt is equal to cos of tzd plus 1 minus cos p into cos of latitude into cos of declination. Now let us understand the terms one by one. The first term which you see is the meridional zenith distance, that is the mzd. Now before I explain the remaining part, let me explain to you a little bit the relevance of X meridian. I told you that nowadays it is practically redundant, but in the olden days, the X meridian method was in use. It was helpful to us. And the reason for that was that at the time of meridian passage, if there is any reason, cause, or interruption because of which a Marpa site cannot be obtained, it could be that it was raining at the time of meridian passage, or the sun or the celestial body was covered with clouds. You could not take a sight at that particular instant. Now, Marpas is an instant. So if you miss that instant, then the meridian passage sight is not possible. It happens only once in a day for the sun at the noon time. So if you miss that instant, the Marpa sight cannot be obtained. Now, it was very important in the olden days to get a Marpa site because our passage calculation, which is also known as day's work, the passage calculation or day's work was based on the noon position, the Marpa's position, and we used to calculate the distance traveled, distance made good, engine speed, all these things, the distance remaining, what is the fuel. A noon report was prepared every noon, giving a full summary of the passage for the last one day, and it was sent to all the concerned parties, the owners, the managers, the charterers, all these parties. So if you missed the Marpa side, the day's work calculation will get affected. Nowadays, we are not bothered because we are getting a real-time position from GPS, and the day's work can be easily calculated from 1200 to 1200, whether you take a sight or not, whether there are clouds or not, whether there is rain or not. But in the olden times when GPS satellite positions fixing was not there, this was the only method with which the day's work could be calculated. So in case a Marpa site was missed, the only other option available to us to get the MZT. See, the Marpa site gave us the MZT, meridional zenith distance. Then This MZD was combined with declination to get the observed latitude. So we wanted a way to get the meridional zenith distance in case the Marpa site was missed. And this is why the X meridian method was used. So we can calculate the MZD, though it is not a Marpa site, it is taken before or after meridian passage. It is not a Marpa site, but still using this we can calculate the MZD, and this MZD can be combined with declination in the same way as was done in a Marpa's observation to get the observed latitude. So that was the whole purpose of X meridian. So cos of MZD is equal to cos of TZD, that is the true zenith distance. It has been calculated already from the true altitude of the body, plus 1 minus cos of P. P is available to us. We had calculated the LHA, which gave us the value of P, into cos of latitude into cos of declination. The latitude used is the DR latitude. The declination is available from the almanac. So all the terms on the right hand side are available to us. We put them in the formula. Using the scientific calculator with a single step calculation, we can obtain the MZD. So this is again a very important formula, not to be forgotten. Make sure that you apply this formula correctly. Now, once you get the MZD,
Sir,
you can
in
combine the MZD and the declination exactly in the same way as we did in a Marpa's observation. Any doubts, beta? Go ahead.
sir, in Merpa's calculation, we did 90 minus true altitude will give us mean zenith distance, but here we are applying the formula. Why is that difference?
That's because this site is not taken exactly at meridian passage time. This is taken before or after meridian passage time, beta.
Okay, sir.
Okay. If Marpas was available to us, we will of course prefer the latitude by meridian altitude, Marpas site. This is used only when Marpas cannot be taken.
Okay, sir.
Okay.
सर इसमें ट्रू एल्टीट्यूड का डायरेक्शन सर सेम है अजमत हो जाएगा सर इसका
Exactly, beta. Exactly. As we did in Marpas observation, the true
यस
altitude was named same as azimuth. Exactly same way we will do here.
यस check में सर there is one doubt there you written there 3TTT so I was
Right.
confused sir
Okay. Let us complete this method. Then I will
yes sir
revise TTT once again.
yes sir
Sir, sir, in Merpa's, we did we combined MZD and lat declination to get the latitude, right? But
That's right, beta.
in those scenario, we had plus or minus. So, but here we have only plus, right? How can
That's
we do?
correct, beta. In Marpas, you are combining MZD and declination. If both were same names, you were adding them. If both were opposite name, you were subtracting the smaller from the bigger, right?
Yes, sir. Yes, sir.
Exactly same thing is done here also, beta. When we combine MZD and declination here, we will follow the same principle, addition or subtraction.
Okay, sir. Okay, sir.
Okay. Only additional thing is here we are getting MZD from the formula. In Marpas, MZD can be obtained directly from the site.
Okay, sir.
Okay. Latitude by meridian altitude observation. And once you combine them, we obtain the observed latitude. So exactly in the same way as we had the observed latitude, we get the observed latitude. Now the combining was by giving a name to the MZD. We had done a shortcut method. You first give name to the true altitude. The name to true altitude is the same as the azimuth of the body in whichever direction the body is. North of the observer or south of the observer, the same name is given to true altitude. and opposite to that is given to TZT as well as MZT. So once the MZT name is there, you have the declination name given in the almanac. Same names you combine, opposite names you subtract the smaller one from the bigger one and retain the name of the bigger one. It gives you the observed latitude. Now up to here, this was similar to the Marpas observation, but after this there is a difference. The difference is, number one, the observed latitude which we got in a Marpas observation was also the fixed latitude. The observer has to be somewhere on that latitude only. But in this case, the observed latitude is not the fixed latitude. Why not? Because in this case, the azimuth of the body is not exactly north or south. The azimuth is close to north or south, but not exactly north or south. Because the body is not on our meridian, the body is close to the meridian. If the body was on the meridian, azimuth will be north or south, and the direction of the PL will be exactly east-west. Anywhere on that PL, you will be on the same latitude. But in this case, the body being not on the meridian, azimuth will not be exactly north-south. Similarly, the PL also will not be running exactly east-west. It will have some different direction, and that is why, depending upon where you are on the PL, the latitude is going to change. I will show you with a diagram also in the next slide. But to remember, the observed latitude, what we get in the X meridian method, is not our fixed latitude. Then how do we use it to obtain the position line of the observer? So for position line, we have to calculate the azimuth of the body. The azimuth as usual will give us the direction of the position line, and we will plot that PL on the chart. So for azimuth, we use the ABC method. A is equal to tangent latitude upon tan P. B is equal to tangent latitude upon tan C. And then we use it in the tan azimuth 1 by C into cos lat formula to get the azimuth of the body. Once the azimuth is obtained, we know the direction of the PL and we can plot that PL on the chart. Which are required to plot the position line. Once these two are known, we can plot this PL on the chart or in our plot. So beta, any doubt in the method now? You have the full procedure, information given, stepwise method and the answer obtained. Any doubt coming anywhere? Good beta, very good. Let's move ahead. Let's see the X meridian plot in the diagram. Now, the reference position where the X meridian PL is plotted or drawn or passes through is the DR longitude and the observed latitude. So this is the reference position, observed latitude, which we calculated from the Marpas formula, the X meridian formula, and the DR longitude. This is the position from where the PL is going to pass. Now, after plotting these two, we plot the azimuth of the body. The body is close to the meridian, so let's assume our celestial body is here. The direction in which the body is represents the azimuth of the body, and perpendicular to the azimuth is going to be our PL. So the green color line with arrows on both the sides represents the position line or the LOP. Now you can see that the observer or the vessel can be anywhere on this PL, and uh, if it is at any point on this PL, it is possible that the fixed latitude may be different from the observed latitude. Observed latitude just gives you a reference position from where the PL is passing. It does not give you the fixed latitude in this case. So depending upon where you are on this PL, which we will find out when we have a second PL, wherever the second PL crosses it, that will be our fix. So depending upon at which point you are on this PL, the latitude is going to differ from the observed lat. So this is the X meridian plot. Clear, beta? Any doubts? Very good, beta. Great. Now, one important thing not required right now in these X meridian questions, but the concept should be clear in your mind. It will be used in star identification question. The concept is used in star suitable for sight questions, and may also be asked to you in orals. Now, I told you that this X meridian method is used when the body is close to the meridian. Now, the next doubt which comes to the mind is, how close is close? Somebody could feel if the azimuth of the body is 355, it is close. And somebody would say, no, it's gone far away. The Marpas azimuth should be 000 or 360, it's at 355, it is too much. So how close is close? Or in other words, what decides whether a body can be observed and the site can be solved using the X meridian method at a particular time or not? Now, I also told you that this X meridian method has some restrictions as compared to the intercept method. Intercept method does not have any restrictions at all. It can be used at any time other than the Marpas. The X meridian method, on the other hand, has some restriction. It can be used only for a certain period of time. To give you an example, let us say if the meridian passage of the sun was at 1200. Now, for using X meridian, there is a particular band of time, a period of time in which it can be used. Just to give you an example, if that band or period is 15 minutes, so 15 minutes before Marpas and 15 minutes after Marpas, that is the period in which X meridian can be used. If the body has gone outside that period, the time has moved outside that period, the X meridian method cannot be used in that case. What should be used in that case? The choice is intercept method. So if the body has gone out of this limit, then we can use the intercept method. Now, how to find the X meridian limit? For finding the X meridian limit, we have the X meridian tables. They are there in the Norris tables. Let me show the tables to you. You can see the X meridian table 1 on the slide now. There are total 4 X meridian tables, table 1, table 2, table 3, and table 4. In the olden days when we did not have the calculators, then all these 4 tables were used to work out a X meridian site. But nowadays the calculations are done with scientific calculators. So we do not require table number 2 and 3. Their purpose is solved using a calculator, but we require table number 1 and table number 4 to obtain the x meridian limit. So let us see now, how do we obtain the x meridian limit for a particular body? Now, if you see in this x meridian table number 1, you can see on the horizontal axis we have the declination. This is the declination of the celestial body whose site is being taken. And on the vertical axis, you have the latitude. This is the latitude of the observer. So this table is entered using the latitude of the observer and the declination of the body. Now let's assume that the declination was 40 degrees and the latitude was 10 degrees. So 10 degrees latitude and 40 degrees declination, the table gives us a value of 2.96. This is also known as factor A. You can see it here. It is mentioned as factor A. So we have obtained the factor A from X meridian table 1. In this particular example, we have taken 40-degree declination and 10 degrees latitude, and it comes to be 2.96. After obtaining this factor A, we enter into table number 4. Any doubts in table 1, beta? Clear?
Clear, sir.
Very good, beta. You see the table number 4 on the slide now. This is X meridian table 4. So in this table 4, we enter with the factor A, which we got from X meridian table 1. So you can see this table gives the limits for using the X meridian tables. The limit is in minutes of time before or after meridian passage. So you can see the factor A mentioned in this column, starting with 30, 25, 20, 15, so on, and going up to 0.6.
Sir, voice is not coming. Sir, voice is not coming, sir.
Sir, you're inaudible.
Limit for our example.
Sir, your voice is not coming, sir.
Okay, can you hear the voice now?
Now
Yes, sir.
we can hear, sir, for past
Yes,
1 minute. We couldn't hear. 1 2
Yes,
Okay,
sir.
beta. All right. Give me a minute.
From this table only we can start, sir, because we
Okay,
got
okay.
the
Just a minute. Just a minute. Be You see the table number 4 on the slide now. This is X meridian table 4.
Yes, sir.
So in this table 4, we enter with the factor A, which we got from X meridian table 1. So you can see this table gives the limits for using the X meridian tables. The limit is in minutes of time before or after meridian passage. So you can see the factor A mentioned in this column, starting with 30, 25, 20, 15, so on, and going up to 0.7 in the last column. And with this factor, you have the maximum interval given in minutes of time. So let's try to find out the limit for our example. We had the factor A as 2.96. So you see it starts with 30, 15, 10, 7. Go in the next column. 6, 5, 4, 3.5, 3, 2.8. Now the value which we have nearest to our value was 2.96. The nearest one which we have here is 3.0. So 3.0 gives us a limit of 32. This basically means 32 minutes before or after meridian passage. So it tells us that 32 minutes before Marpas and 32 minutes after Marpas is the time period which in which the Marpas method, the X meridian method can be used. So if our Marpas was at 1200 hours, 32 minutes before, that's 11:28 and up to 12:32. From 11:28 to 12:32, the meridian passage, the X meridian method can be used for obtaining a position line. If the time has gone outside this window, let us see it is 12:33 now. So it has gone outside the X meridian limit. This is known as X meridian limit, in short also known as EML. If the body or time has gone outside the X meridian limit, then this method is not recommended. This method will give us substantial errors. It is not recommended and we should not be using this method then. In this case, we should be using, if the body has gone outside the X meridian limit, we should be using the intercept method instead.
So how do we find out it's gone outside the limit?
Beta, the time for the site will be known to you, right? So
Sir.
you check the time of the site and you check the X meridian limit. If the time is within limits, you can use X meridian. If the time has gone outside limit, you cannot use X meridian.
That is with the GMT time, sir.
Okay, let me give you an example. Let us see let us assume that on one particular day, the meridian passage time was 1200 hours. Okay, let's say it was LMT meridian passage 1200 hours and you had the limit as 32 minutes, right? So 1200 plus and minus 32 gives you the window within which the site can be worked out. So the window is basically between 11:28 to 12:32, right beta?
Yes, sir.
Now, if you take the site between 11:28 and 12:32, any time in this particular window, you can use the X meridian table, X meridian site, X meridian method can be used. If the time has gone outside this window, it is before 11:28, let us say the time is 11:15, then you cannot use X meridian. Or if the time has gone beyond 12:32, let's say the time is 12:45, then you cannot use X meridian method.
Okay, sir.
Okay, any more doubts, beta?
Sir, can you quickly again one more time explain table for sir power cut here, sir? There's no logged in
Okay,
anymore.
okay, beta. From
Sir,
table
also,
one,
you're sharing your
uh,
screen, sir. I can see that.
yeah, I'm sharing, beta. What about other people, beta? Can you see my screen?
Yes, sir.
Yes, sir, we can see, sir.
Okay,
Okay, sir.
so
Just log
beta,
out and log in.
yeah, please do that. It'll be visible to you. Okay, I'll repeat once
Yes,
again,
sir.
beta. You get factor A from table 1 and with that factor A you enter into table 4. You can see in the first column factor A values are given. Along with factor A values you will see the interval given in minutes. For factor A value of 30, the interval given is 6 minutes. So this interval is the X meridian limits in minutes of time. So from the meridian passage time, this many minutes before that time and this many minutes after that time. It is written here on top of the table. Minutes of time before or after meridian passage, X meridian can be used. Clear, beta?
Understood, sir.
Getting clear?
Understood, sir.
Okay, beta. Great.
Excuse me, sir.
So the
Now these tables, beta, X meridian tables are there in the Norris table also. And I had sent you a shortened version, 25 pages of nautical tables. These X meridian tables are included in those also. So you can take a printout and refer to them. You will get the X meridian tables.
so according to this, the minimum time for any body to pass, the limit is minimum is 6 minutes.
Yeah, that's right, beta.
Okay, sir.
Sir, in this table, the expedient table 1, we have for few latitude and long declination, it's empty and it's blank left. So what does it mean?
Okay, all right. Now, if you refer to table 1, you will see there is a band where no values are given. It's blank. So if by chance you get your value in that zone, in the blank zone, it basically indicates that the X meridian method cannot be used for that particular observation. So you will have to switch over to intercept method, beta.
Sir, in practical on board, first we will practically calculate this declination and then we can confirm whether it is passing before Merpass or after Merpass.
Beta, you will see two things. Number one, practically on board, first you will try to take a Merpass site. Let us say sun's meridian passage is happening at 1200. You will try to take a site at 1200. If you can take that site, you will use the meridian passage method and the PL is obtained. End of the story. That's option 1, right?
Okay, sir.
Now let us assume that because of any reason you were not able to take a site at 1200. It's already 1210. Now the other option available to you is the X meridian method. Okay. So what you do now is, do you note the time? The time is 1210. And you now find out the X meridian limit for the sun. How will you find that out? Check the declination of the sun on that particular day for that time. You know what is your DR latitude. Using these two, get factor A from table 1, and using this factor A, get the X meridian limit from table 4. Can you do that?
Actually, for this Merpass calculation, before like in 8 to 12 watch at 10 o'clock itself, we should confirm what is the meridian passage time. According to that, we have to prepare, sir.
That's right, beta. You have to prepare accordingly. So is your doubt resolved now?
In that top, you have given this latitude and declination same name and opposite name. If it is opposite, we have to see in this opposite table.
Exactly. Table 1 is divided into two parts. So in one part, you will see latitude and declination same names. So if you are in the north hemisphere, the declination is also north, you go into that part. The second part of table 1 gives you lat and dec opposite name. So you see which criteria is applicable to you and you go into that part of the table.
Okay. Sir, for example, if you are taking one observe on during this X meridian and at Merpass, we get two observed lat, sir, and two PLs. Will the two
That's right.
PLs will make a fix?
Theoretically, yes, but practically it will not be recommended. The reason why it is not recommended, I'll tell you. See, the azimuth of the body will not be changing much, right? X meridian, the body is very close to the meridian, and at Merpass, it is on the meridian. So the azimuth will be very close. One azimuth could be 355, another azimuth could be 000. When the azimuth is very close, you see the angle of cut between the PLs is going to be very, very small. So with this small angle of cut, the accuracy of the fix will be very low, beta. So it's not recommended.
Okay. Okay, sir.
You should have sufficient time between the observation so that the azimuth changes substantially by at least 20, 30, 40 degrees. Then you get a good angle of cut and a good fix.
Sir, and one more doubt, sir.
Hmm.
Normally, when we are on board in the morning watch 8 to 12, we take one long by Chrome, and at Marpas, we take one Merpas calculation. And after in the noon time, we take intercept. How to run this and make a fix at the intercept time, sir?
Okay. Now, beta, you in the olden days, the procedure, I will tell you what was the procedure. The first thing which you used to take, I'll tell you right from sunrise to sunset, what procedure we used to follow.
Yes, sir.
The first thing which we used to do was taking a amplitude of the sun at the time of sunrise. That gives you the compass error. After that, you wait for the sun to rise at least about 10 degrees. Below 10 degrees, a sight is not recommended. So you wait for the sun to come up at least 10 degrees. So after that, you used to take a longitude by chronometer sight. It will give you one PL. You will not have a fix, only a single PL. Then you wait for meridian passage. You have calculated the meridian passage time already. So at that time you are standby. You take a meridian passage sight and you get a observed latitude, which is also your fixed latitude. Now what you do is the morning long by chron PL is transferred to the noon time. How do you transfer it? By applying the course and distance. We will see this when we do plotting. So you put your courses and distances and you apply a run and you transfer it to the noon time. When you transfer the long by chron PL to noon time, you get a noon fix because there are two PLs now. Their intersection point gives us a noon fix. With this noon fix, we move on and we continue our DR navigation, dead reckoning navigation. At the time of sunset, again a second amplitude to get the compass error. After sunset, now you calculate the twilight time. And in that twilight time, you take a star sight. Now, when we take a star sight, a lot of stars are available. So we used to consider take at least 3 stars, take their altitude, work out the sight and plot them all. So immediately you will get a fix. So that was the evening fix. With that evening fix, you do DR navigation till the next morning. So that is the procedure what we used to follow.
So can you explain after the noon what we will do, sir? Can you explain?
Afternoon, beta, you can keep on running DR navigation. Okay. DR navigation can continue till evening twilight. If you want, you can take another site in between using a intercept method.
Okay.
Sir, one more doubt, sir. For example, when you are in ocean passage, some
Hmm.
days we might not, due to the weather condition, we might not be able to see the horizon or the sun or any celestial bodies. During that time, we'll only run the DR for 24 hours until the next fix.
That's correct, beta. Before GPS, we were only dependent upon celestial navigation or terrestrial PLs or terrestrial navigation. If you don't get any terrestrial object, you cannot get any position circle or position line using land object, and you are not able to see the sky, it's cloudy, rainy, you have to do DR navigation.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Any more doubts now, beta?
Because currently we are only taking site for the wedding, sir. That's the reason I'm
Yeah, that's right, beta. That's right. You may be asked about this in orals. So if you can explain the sequence, the surveyor will be happy.
Thank you, sir.
Okay, all right. So that was the X meridian method, beta. So X
Sir,
meridian method is done. Go ahead, beta.
in those days, how they run DR for 24 hours, sir? Because the chart dates, current, all limited,
Okay.
right?
We used to estimate the current, beta. The current was estimated basis the sailing directions, routing charts, okay, and any weather reports which we received. So using these three, you will estimate what is the current in the area. And using that estimated current, you will plot your positions. In chart work, you might have come across, or if not yet, you will come across some questions where they will give you some current. And then they will tell you after 4 hours, the vessel was observed to be at this position. Find the actual set and rate of the current. So those
Yeah.
questions are based on the previous scenario, pre-GPS era.
Okay, sir. Okay, sir.
So that's how it was used to be. Another interesting thing I'll tell you, if you see the sailing directions, beta, many of the ports or many of the coastlines, you will find photographs. So they will have a long, short photograph given in the sailing directions, pilot books, so that you, when you are going close to that area, you can identify. Okay.
Okay.
Like India West Coast, you will see close to Bombay, you will get a picture. They'll say mangroves, lot of trees are there, and they have made a picture. Sometimes these pictures are hand drawn. Okay.
Okay, sir.
So you must have seen that in pilot books. So what was the purpose and use of those beta? The purpose and use was, if somebody is doing DR navigation and not able to get a fix because of any reason, when they make a landfall, looking at that picture and looking out of the bridge window, they used to correlate that is this view which we are looking out of the bridge window matches with what is given in the sailing direction, and they used to find out whether their DR is accurate or not.
Okay,
Okay,
sir.
so that's how people used to navigate. Today it all looks like stories, but that was the thing. This was their 1990 से पहले यही था बेटा. So you can say it's about 30 years back.
Okay, sir. Okay.
Okay.
VHF भी नहीं होगा सर, तो फिर पायलट कैसे आएगा?
No, VHF was there. VHF was there long, long time back. So VHF was no issues.
Okay.
Okay. Great, beta. So let's take a break. Break के बाद let's take a 5 minutes break and then we move on to Polaris.
Okay, sir.
Okay. Okay, beta, are we back? आ गए बेटा वापस?
Yes, sir. Yes, sir.
Okay, all right. So let's move on to Polaris, beta. Now, beta, Polaris, I am going to explain you the concept of Polaris using the rational horizon diagram. Now, I have not yet covered the principle of rational horizon diagram with you. So even if you do not understand it well, just listen to it like a story. Once I cover the plotting part, the side solving part, I will explain the rational horizon diagram in detail. So you will understand it very much at that time. So don't bother too much if you don't understand it. Listen to it as a story so that the concept gets inside, and that will help you to understand and appreciate the method. Okay, beta?
Yes, sir.
Okay. So let's go, beta. Let me put up the presentation. Let's see. Let's now try to understand the Polaris or pole star observation method of obtaining a position line. This is also a very quick and easy method with which the position line can be obtained. It does not involve any formulas, not much calculation, and we can obtain a PL very fast using this method. Now, before we go into the stepwise procedure, we need to understand the basic concept, the underlying concept on which this method is based. Now, for this, we need to make a rational horizon diagram. Let's assume our observer is in north hemisphere, and let's make a rational horizon diagram for him. You can see the rational horizon diagram made on the right side of the screen. At the center of this diagram, we have the zenith of the observer, the point directly overhead represented by alphabet Z. And on the circumference, we have the points N, E, S, W representing the rational horizon of the observer. Our observer is in north hemisphere in this case. Now, when the observer is in north hemisphere, the equator will be south of the observer. Similarly, on the celestial sphere, the equinoctial is going to be south of the zenith of the observer. Equator is projected onto the celestial sphere as equinoctial. Observer's position is projected to the celestial sphere as the zenith. So let's show the equinoctial in our diagram. The equinoctial in the rational horizon diagram always passes from east and west points. So let's draw the equinoctial. You have the equinoctial in the diagram now passing from east and west point, and it is passing south of the zenith. Our observer is in north hemisphere, that's why the equinoctial is passing south of the zenith. The point where the equinoctial crosses the observer's meridian is represented by Q. So you can see the Q point marked in the rational horizon diagram now. Now, since Q represents the equator on the celestial sphere, Z represents the position of the observer on the celestial sphere, this arc of the meridian between Z and Q, the arc ZQ represents the latitude of the observer. So ZQ being the latitude of the observer. Now let us show the pole in this diagram. The pole is 90 degrees away from the equinoctial. So from point Q, I go 90 degrees away, and somewhere here we will have the North Pole visible to the observer. The observer is in North Hemisphere, so the pole which will be visible to him will be the North Celestial Pole. The South Celestial Pole is going to be below his horizon. South Celestial Pole will be 90 degrees south of the equinoctial or the Q point, and it will be below the horizon of the observer. So we have the pole shown in the diagram now. Let's mark the pole with point P. Now with the pole visible in our diagram, let's now concentrate our attention to arc NP. N represents the north point of the observer's horizon. N point is on the rational horizon, and P point represents the celestial pole, north celestial pole. This arc N to P is basically the altitude of the pole, or it is also known as the elevation of the pole. You see, N point is on the horizon, P is the celestial pole. So N to P marks the arc of the vertical circle contained between the pole and the horizon. This is the definition of altitude. So NP is the altitude of the pole, also called as the elevation of the pole.
Also latitude, correct?
Now, we are aware that this celestial pole is 90 degree away from the Q point on the equinoctial.
Sir, one doubt. Sir.
We are also aware that the N point, which is on the horizon, is 90 degree away from the zenith of the observer. So now you see point P is 90 degree away from the equinoctial, that is Q. Point N is 90 degree away from the zenith. So the difference between Z and Q will be the same as the difference between N and P. Or in other words, the arc ZQ will be equal to the arc NP. So with this, we come to know that this NP will be equal to the latitude of the observer.
Latitude or either altitude also? Both. Correct, sir.
This is known as the altitude of the pole, also called as the elevation of the pole, and this is equal to the latitude of the observer.
Okay, sir.
Okay, clear, beta?
Yes, sir.
Okay. In other words, you can say that the altitude of the pole or the elevation of the pole straight away gives us the latitude of the observer. So we get a very easy method to obtain the latitude here. If we can take the altitude of the pole, it will immediately give us the latitude, which is a very simple and easy way. The only problem here is the celestial poles are not lit up. If they were lit up, there was some star or some light there, then we would be able to take their altitude and get our latitude very easily. But unfortunately, the poles are not lit up. But there is one star, special star, which is very close to the north celestial pole. There is no such star close to the south celestial pole, but we have one star which is very close to the north celestial pole, and that star is the Polaris. Other name for it is the pole star. Since it is very, very close to the north celestial pole, it is called as the pole star. Now, this star is having a declination of 89 degrees and 10 minutes. So it is within 1 degree of the celestial pole. So with this star being so close to the pole, if we take the altitude of this particular star, then it can very nearly give us our latitude. So this is the concept behind the Polaris or pole star observation. Pole star being a special star very close to the north celestial pole, if we take the altitude of this pole star or Polaris, it gives us very nearly the latitude of the observer. If the pole star was exactly at the same place where the north celestial pole is, in that case it would give us the latitude exactly, accurately, without any difference or error. But since it is not exactly where the pole is, it is slightly away from the pole, the altitude what we get from the observation of Polaris is also not exactly same as our latitude. There is a small difference between the two. Now this difference which is there between the altitude of the pole star and the latitude of the observer is tabulated in a table in the nautical almanac. We can obtain that difference from there. We can apply that difference to the altitude of the pole star, and once applied, it gives us our latitude. So this is the basic concept behind the Polaris observations. We have the Polaris table or the pole star table given in the nautical almanac, which provides us this correction, which can be applied to the altitude of the pole star to easily obtain the latitude of the observer. Any doubts coming in this, beta?
Yes, sir.
Sir, regarding this pole star, is the Polaris will be always the pole star, or there will be any change in the stars?
No, beta, Polaris is not exactly where the pole is. Polaris is slightly away from the North Celestial Pole. So sometime it can be slightly higher than the North Celestial Pole, sometime it can be slightly lower than the pole. It is very close.
I understood, sir. Regarding this Polaris, it is said some for some years this Polaris will remain as pole star. After some years, some other star will replace it. Is it true, sir?
Yeah, that's correct, beta. That's correct, but that will happen over thousands of years, not so frequently. This happens because of the precession of the equinoxes. The axis of the Earth is changing its direction basically, and that is why right now where the axis points, pole star is very close to that.
Sir,
Okay, sir.
at what latitude we can take this Polestar site, sir? There is a At how much latitude we can take this?
Okay, beta, it is recommended that the uh, latitude up to which you can use this Polaris observation is about 70 degrees. Okay, अभी हम टेबल देखेंगे तो टेबल में भी आप देखोगे the values are given, I believe they are given up to about 68 degrees. So beyond that, if you are in higher latitudes, then the Polaris site cannot be taken.
Okay, sir. That is the limit, but I'm asking from which latitude we can take this site.
You
Starting.
can take it from any latitude, beta. In the northern hemisphere, Polaris will not be visible in the southern hemisphere. So in the northern hemisphere, from zero, that is equator, up to about 68 degrees north. Okay, you can take the Polaris site.
Okay, sir. Okay, sir.
Okay, all right. So Let me now take you to the Polaris table, beta. Let me show you. This table basically gives us the correction which is to be applied to the altitude of pole star to get the latitude. So let's see that.
Sir, one more doubt.
Go ahead, beta.
Sir, when we are in southern hemisphere, we have learned somewhere, I think, this southern cross is used as polar south pole. Sir, is it true, sir?
No, cannot be used, beta. It is far away from the South Pole, not close.
Okay, okay,
That's why you do not see any table for the Southern Cross. Okay.
okay, sir.
Okay. Now this correction which we apply to the altitude of the pole star or altitude of Polaris to obtain our observed latitude is available in the almanac. We have a Polaris pole star table. You can see the Polaris pole star table in the 1992 almanac on the screen now. It's given on page number 274. Now, if you look carefully in the table, you will see that the table is entered with LHA Aries. Every column represents a range of 10 degrees. 0 to 9 degrees is the range in the first column, then 10 to 19, 20 to 29, 30 to 39, 40 to 49, and so on. There are total 36 columns representing 360 degrees of LHA Aries. So for entering in the table, we have to first find out the LHA of Aries. The time of observation is given to us in the question. Using that time, we obtain the GHA of Aries from the almanac. The longitude is given to us in the question. Using the longitude, we obtain the LHA. Now, once the LHA is obtained, we can enter into the respective column as per LHA and get the corrections. The top part of the table gives us the A0 correction. Then the second part gives us the A1 correction. The third part of the table gives us the A2 correction. And the bottommost part gives us the azimuth of the pole star. Now let's see how do we obtain the values of A0, A1 and A2 corrections. Let's assume for the sake of an example that the LHA of Aries in a question is obtained as 65 degrees. So with LHA Aries 65, first of all, we have to select the column. You can see the first column is from 0 to 9 degree 59, then the next one 10 to 1959 and so on. So 65 degree is going to fall in this particular column. 60 degrees to 69 degree 59 minutes. So we enter in this particular column of the table. And when we go down, the first value which you see here, 0 degrees 16.8 minutes, this is for exactly 60 degrees of LHA. For 61 degrees, it is 17.2, 62 degrees, 17.5, and so on. When you go up to 65 degrees, you see the A0 correction. This top part is for A0 correction. The A0 correction comes out to be 18.6 minutes. So for 65 degrees LHA Aries, the A0 correction is 0 degrees 18.6 minutes. Now another thing which you need to pay attention to is that in case if the LHA Aries was 65 degree 30 minutes, 65 degree 30 minutes, you see now the value for 65 is 18.6 minutes and the value for 66 degrees is 19.0 minutes. For any intermediate value, we will need to interpolate between these two figures. So for 65 degree 30 minutes, the value will be exactly midway between 18.6 and 19.0, and that would be 18.8 minutes. So
Okay, sir.
this is how we refer to the table and obtain the A0 correction. Interpolation may be required if you have a LHA value between any 2 degrees. Now moving on to the A1 correction. For obtaining the A1 correction, we continue in the same column which we entered using LHA Aries. So we had taken an example of 65 degrees LHA Aries. For A1 correction, you continue in the same column. And when you come to the second part of the table, you see the A1 correction listed here. This A1 correction is given against the latitude of the observer. So the dr latitude of the observer is given to us in these questions. In case in some question the dr latitude is not given, then in that case the altitude of Polaris can also be considered or taken as the dr latitude. So we enter with the latitude, and against the latitude closest to our dr lat, we pick up the A1 correction value here. The latitudes are given as 0, 10, 20, 30, 40, 45, 50, and so on. You can pick up the nearest value, which is the nearest value to your dr latitude. And if you have a look at the A1 correction also, there is no interpolation which is required in this part of the table. You can straight away pick up the A1 correction against your nearest latitude and it can be used.
So can you tell again if the latitude is not given, what to do, sir?
Beta, you can take the true altitude of Polaris and use it as your dr latitude.
True altitude. Okay, sir.
Okay, that's because they are going to be very close. The difference is not going to be much.
Okay, sir.
Okay. Now moving to the third part of the table. If you follow the same column which you had entered using LHA Aries, after A1, the next correction which is given here in the table is the A2 correction. In the third part of the table, you will see the A2 correction. A2 correction is given against the month of the year. You can see the month on the vertical axis on the left side. So depending upon in which month the site was taken, the observation was taken, you can go into that row and pick up the A2 value from the third part of the table. Now moving further, if you go down to the bottom part of the table, the bottom part of the table gives you the azimuth of Polaris. So azimuth of Polaris can be straight away read off from the table. We do not need to calculate it like other celestial bodies. It can be straight away picked up. The azimuth of Polaris is also given against the latitude. So the latitude which is given to us, dr latitude which is given to us in the question, we pick up the nearest value of the latitude to our dr lat, and then in that row the azimuth of the Polaris or pole star can be picked up.
Let's say if we have a latitude of 45 degree,
That's
so
right,
it,
beta.
so it would be
45 degrees.
359.5, correct, sir?
Yeah, you can round it off. The only accuracy what we take is only one place after the decimal. So you can round it off to that value.
Okay, sir. So that 45 degree should match with the LHA Aries value, which is 65 degree table, correct?
Exactly, beta. Exactly. So the vertical column which you entered from the top using LHA Aries has to remain the same for all the four A0, A1, A2 and azimuth.
Okay, sir.
Okay, so clear beta? Is the table clear? Any doubts in the table?
Sir, just the 65 degrees you said, no, sir, for LHA Aries, it is 18.6. Is that right, sir?
Uh, 65 degrees. Just a minute, beta.
Yes, 18.6.
Okay, I've zoomed in. Okay, so for 65 degrees, it is 18.6.
So if it is having some minutes, we have to interpolate between these values.
That's correct, beta. Like you see, for 66, it is 19.0. So anything between 65 and 66, you will need to interpolate. And once you have interpolated, you can round off to one place after the decimal. No need to go to more places after the decimal. Round it off to this accuracy.
Okay, sir. Thank you.
Okay.
सर ये जो 10 है सर अंडर लैटिट्यूड 10 degree and the 0 degree is the same value, sir. So
Okay.
which column to take, sir, in that case?
Say again, beta, what was your doubt?
So under 10 degree,
Right.
yeah. The first value is 0 degree 17.5,
Right, beta.
and also in 0 to 9 degree में last में 10 degree में 0 degree 17.5 है.
Okay. Beta, basically the last value given in one column is the same as the next value given. जो first column की last value है, that is also 10 degrees. And the first value of the next column is also for 10 degrees. Okay.
Yes, sir. So which column we should select?
Anyone, beta. For exactly 10 degrees, you can go anywhere.
Okay, any column is okay.
Okay.
Because starting में जो column लेंगे वही end तक we have to use the same column, right?
Yeah. Oh, if the value exactly matches to 10 degrees, practically it will not happen. You will always have some minutes or seconds. So it will not happen. But yes, if it happens, then you can pick up any column of your choice.
Okay, sir.
Okay. There may be a slight difference. 0.1 difference may be there in those columns, but that is acceptable.
Right, sir.
Okay.
Sir, in the bottom of this page, we have correction I0. What is it, sir?
In the bottom beta, they give you the formula basically. The latitude is obtained as apparent altitude corrected for refraction. This is basically the true altitude. Apparent altitude of a star, when you correct it for refraction, it becomes the true altitude. So latitude can be obtained as true altitude minus 1 degree plus A0 plus A1 plus A2. So this is what we will be doing when we do the Polaris sight. This is exactly the formula which we'll be using.
That is minus 1 degree, sir, not I.
Yeah, that's minus 1 degree beta.
Okay.
And it will give observed latitude, sir.
It will give you the observed latitude. That's right.
Yeah.
Okay, all right. So let's see the method now. Now, having understood the table, we can now obtain the values of A0, A1, A2 from the table. Let us now see how do we solve a Polaris sight. First of all, let's see the information which is given to us in these questions. The information provided is the date and time of observation in GMT or the chronometer time. If chronometer time is provided, AM PM indication is given to us, and we use that to resolve the chronometer ambiguity. Second information which is given is the sextant altitude of Polaris, the index error of the sextant, and the height of eye required for dip correction. Along with this, the DR position of the ship is also given. Now the first step which we follow is we find out the GHA value, GHA Aries value from the almanac. We get the hourly GHA from the daily page. we apply or add the minute and second increment from the increment table and get the GHA of Aries, accurate GHA. To this, we apply the DR longitude. DR longitude is given to us in the question, and we get the value of LHA Aries. Now, next step, we apply the corrections to the sextant altitude of Polaris. Index error is applied. If it is off, we put it on, means plus, and if it is on, we put it off, means minus. The height of eye gives us the dip correction, and dip correction is always negative. Once we apply the index error and the dip correction, we get the apparent altitude of Polaris. To this apparent altitude, we apply the total correction, and that gives us the true altitude of Polaris. Once true altitude is obtained, we get the correction A0, correction A1, and correction A2 from the Polaris tables. And all these corrections are positive corrections. So to the true altitude, all these three corrections are added, and we subtract 1 degree from the total to get the observed latitude. You can see the formula also coming up. Observed latitude is equal to true altitude plus A0 plus A1 plus A2 minus 1 degree. Now to plot the PL along with the observed latitude, we also need the azimuth of Polaris. The azimuth is found using the bottom part of the table, bottom part of the Polaris table. Azimuth is picked up from there. And once we have the azimuth and the observed latitude, we can now plot the pole star position line. The position line is perpendicular to the azimuth, as always in celestial navigation. So once the azimuth is known to us, the PL is plotted perpendicular to it.
Sir, in the Nautical Almanac Polaris table below, it is mentioned latitude is equal to apparent altitude, but here we said true altitude.
Beta, with apparent altitude, there's something given in the bracket also. So what is that?
Corrected for refraction, sir.
Right. Now Polaris is a star. The only correction which is applicable to a star, the total correction, is the refraction correction, beta. So stars do not have any semi-diameter, or they do not have any parallax. So once you correct the apparent altitude for refraction, it becomes the true altitude.
Okay, sir. So there is no total correction.
That's correct, beta. The total correction for stars is same as the refraction correction.
Okay, sir. Okay, sir.
Okay, beta. Great. So we have the Polaris method now. Any doubts coming anywhere in this, beta? Very good, beta. Great. Great. Very good.
Drawing this PL line is same as lat by meridian altitude method, right?
Yeah, same. I'll show you.
Okay, sir.
Let's now make the plot of the Polaris observation. Now, for plotting the PL, we draw the DR longitude. The longitude used is the DR longitude. The latitude used is the observed latitude, which we obtained from the Polaris site, working out the Polaris site. So observed latitude obtained from the Polaris site, and the DR longitude gives us a reference position from where the PL will be passing. Now on this point, we mark off the azimuth of Polaris, or the pole star. Let's assume the pole star is here. So the red arrow shows the azimuth of the pole star, and the direction of the PL will be perpendicular to the azimuth of the body. So you see the green color line having arrows at both the ends represents the position line in case of a Polaris observation. Now you can clearly see if the azimuth of the pole star is exactly 0.0, azimuth is exactly north, In that case, the PL will be running in the east-west direction, and the PL will then also be our fixed latitude. Now, there is a possibility that the azimuth of the pole star may be exactly 0.0. And if that is so, azimuth exactly 0.0, the PL observed latitude becomes the fixed latitude also. So that's a special case in Polaris.
Okay.
So any doubts in this beta Polaris site? Great beta, very good. So that was the Polaris site. Now, let me take you to one more concept in celestial navigation, which is rarely coming in exams, but you may sometime come across. This is the concept of back angle. Okay, so back angle observation, how the back angle is to be corrected. So let's see that beta. Let me show you. Let's now understand the concept of back angle. Now this back angle is practically redundant nowadays, no more used. But in the olden days when we were dependent upon celestial navigation for our position fixing, back angle was used whenever the situation demanded. So let's try to understand what this back angle technique is and how does it help us to obtain the altitude of a body. Now this back angle concept is used in those scenarios when the horizon is obscured due to any reason. The reason could be rain, it could be fog, it could be clouds, or there could be a coastline visible to you. Now, because of all these reasons, it is possible that the horizon may not be visible. Now, if the horizon is not visible to us, then we will not be able to take a celestial observation. We will not be able to take the true altitude of the body. For true altitude, we need to have the center of the body as well as the horizon both visible to us, and we measure the angle between these two using the sextant. So in these scenarios when horizon is not visible, it will not be possible for us to take a normal sextant altitude of the body. Now, since in the olden days it was very important to take the sight, that was the only method available to us in open sea conditions where there were no land-based terrestrial navigates. This was the only means of position fixing. And if we are not able to take a sight, the vessel will be in doubt where the actual position is. So we tried our best to obtain the position line in whatever situation we were in. Now, in these scenarios also, it seems we will not be able to take the sight, but there is one possibility which is available. And that possibility is if the horizon on the opposite side is visible to us. Let me give you a practical example. Let us say you are coasting and you are coasting on, let us say, Indian West Coast. You are passing Mumbai and moving in the northwest direction. Uh, Now you have the coastline on your starboard side. Now let us say the sun rose and at about 9 o'clock, 10 o'clock, you went on the bridge and you wanted to take a sight, but you will have the coastline and the horizon will not be visible to you. Now this is where the back angle technique can help you. Instead of using the horizon in the direction of where the body is, we can use the horizon opposite to it and obtain the altitude of the body. Now, how is it done? Let us try to understand using a diagram. You see this diagram now. We have the earth in the diagram. We have the earth. Then we have the center of the earth at this particular place. We have the observer at point O. Observer has got some height of I also. You can see he is above the surface of the earth. C represents the center of the earth. And the celestial body which we are trying to observe is this particular star named as X. Z represents the zenith of the observer. Now, this line which you see passing from C, R dash, passing from the center of Earth, represents the rational horizon of the observer. Rational horizon plane passes through the center of the Earth. You can see it passes from the Earth center, and every point on it is 90 degrees away from the zenith of the observer. So this is our rational horizon. Now, from the observer's eye, if we draw a tangent to the surface of Earth, from the observer's eye, we draw a tangent to the surface of Earth. You see, this is the tangent in one direction. This is represented by OV dash. This represents the visible horizon of the observer. If you see on the opposite side, then from the observer's eye, you draw a tangent. You see OV is the visible horizon of the observer. Now, if you draw a line or a plane passing from the eye of the observer and parallel to rational horizon, you see this is the observer's eye and we have the rational horizon as R dash. This is the plane of the rational horizon. So from the observer's eye, if you imagine a plane which is parallel to the plane of the rational horizon, which is represented by S dash in the diagram, this is the sensible horizon of the observer. This is the definition of sensible horizon of the observer. So we have the sensible horizon also here represented by S dash. Now the situation is such that in the direction where the body is, you see this body X is in this particular direction. In a normal scenario, we would have used the visible horizon OV dash to obtain its altitude. But the situation is such that this particular horizon is not visible to us. There may be coastline, rain, fog, clouds as discussed earlier. So this side of the horizon is not visible to us. So that's why I have put a cross over here. But the horizon on the other side, which is OV, diametrically opposite to the direction in which the body is, exactly reciprocal, opposite, this side horizon is visible to us. So if you have coastline on one side and the other side is clear, you will be able to see the horizon on the other side. So horizon on the other side is visible to us. This is the scenario, or this is the situation where the back angle method can help us. So even though the horizon in the direction of the body is not visible to us right now, we can still obtain the altitude of the body using the back angle technique. Now let's try to understand what this technique is. Now in a normal scenario, if this coastline or rain or fog or cloud was not there, and the horizon was visible to us, OV dash horizon in the direction of the celestial body was visible to us, we would have obtained this particular green color angle using our sextant. This is the angle which we would have obtained. This is the angle between the center of the body, represented by OX, and between the visible horizon of the observer, represented by OV dash. So this angle XOV dash is what we would have obtained from our sextant. Now, once you obtain this angle, the correction what you apply to this angle after the instrument error, after the index error, the next correction which we apply is the dip correction. The dip correction. Now, what is the dip correction? Dip correction is basically the angle between the sensible horizon and the visible horizon. Let me show you here in the diagram. You see this particular maroon color angle. This is the angle between the sensible horizon, represented by SS dash, and the visible horizon, represented by OV dash. This is known as the dip angle. The full name of the dip is dip of the sea horizon. Basically, it tells us how much is the visible horizon dipping below the sensible horizon. That's why we call it dip. So we would have applied the dip angle or the dip correction to this angle which we have earlier obtained. We have seen the dip correction now applied here. Now, once you apply this dip correction, the maroon color angle is subtracted. You would have obtained angle XOS dash. This was the apparent altitude of the body. So to the apparent altitude, we would have applied the total correction and we would have obtained the true altitude. This would be the normal method when the horizon is visible to us. But now we do not have the horizon available to us because of any of these reasons. So we cannot follow this particular method. So what do we do now? Now, since the horizon on the opposite side is visible to us, that is OV, this side of the horizon is visible to us, instead of measuring the angle to the normal horizon, we measure the angle from the center of the celestial body to the horizon in the opposite direction, represented by the blue color angle in the diagram. The blue color angle which you see is the angle between the center of the body and the horizon on the opposite side to which the body is. So we have used the sextant to obtain the angle between the center of the body and the horizon in the opposite direction. Now, obviously, this angle will be more than 90 degrees. A normal sextant altitude would always be less than 90 degrees, but this being a back angle observation will be greater than 90 degrees. Its value will be more than 90 degrees. So if you get a question in your exam where the angle is given as more than 90 degrees, don't think that it is a misprint. It could be a back angle observation. So we have obtained this back angle now. The back angle is obtained. Now, how do we proceed ahead from here? Now, the blue angle which we have obtained is angle XOV. X is the center of the body, O is the observer's eye, and V represents the horizon in the opposite direction. Now, to this angle, after applying the index error, obviously that is the instrument error, we again apply the dip correction as usual. We would be given the height of eye of the observer in these questions. So we get the dip correction and we apply the dip correction to this blue angle. So let us see what happens once we apply the dip correction. You can see the dip correction now represented by the maroon color angle. This is the dip correction applied to the horizon on the opposite direction, reciprocal direction. So once you apply the dip correction, the angle which we have now obtained is this blue color angle. The angle which is available to us now is XOS. And if you look carefully, this particular angle is basically 180 minus apparent altitude. You can see the sensible horizon SS dash. It is a straight line. It is a plane, or in this diagram, it is a straight line passing from the eye of the observer and parallel to the rational horizon. So the angle which we have obtained now, that is the blue color angle, and the angle which we require, which is the green color angle, they will add up to 180 degrees. So if we have obtained the blue color angle, 180 minus this angle would give us the apparent altitude what we require. So 180 minus the blue color angle which we have obtained, we call this also as apparent altitude in the back angle calculation. Once you do 180 minus apparent altitude, you get the corrected apparent altitude. The green color angle is now called a corrected apparent altitude. So once you obtain the apparent altitude, further calculation is easy. It is exactly same as we did before. We apply the total correction and we get the true altitude of the body. So this is how we obtain the true altitude of the body using this back angle concept.
So basically, in the exam question, if they give the section altitude more than 90 degree, we will subtract minus 180 from the apparent altitude to get the true altitude. Correct?
Yes, beta, that's right. That's right.
Okay, sir.
So any doubts in this, beta? Is it clear? Very good, beta. Great. Now there is one more thing to take care here, beta. In case you are having this back angle for sun or the moon. Now there is one more thing which you need to be careful about. If you have a back angle observation of sun or moon and you do this procedure, now as soon as you subtract it from 180 in step number 3, as you subtract it from 180, you get the corrected apparent altitude. Along with this, you have to change the limb of the sun or moon. If the site was given for the upper limb, as you subtract from 180, the upper limb will get changed to lower limb and vice versa. If the site was given for lower limb, as you do 180 minus apparent altitude, the corrected apparent altitude will become for upper limb. So limb is to be changed whenever you subtract it from 180. This is because when you change the horizon, subtracting from 180 basically changes the horizon. When you change the horizon, the limb of the body changes. What is upper limb in one direction will become the lower limb on the opposite direction.
So can you tell me one more time, sir, how do we use for the questions in the?
Beta, what I told just now, you have doubt in that?
Yes, sir.
Okay, just remember one thing, beta. If you have a back angle of sun or moon,
Okay, sir.
then they will also tell you it is the upper limb altitude or the lower limb altitude, right?
Yes, sir.
So when you subtract it from 180, you change the limb. Upper limb will become lower limb will become upper limb.
So if they in the question, if they mentioned upper limb, then we will refer in the almanac lower limb.
Right, you will apply the correction for the opposite limb, that is the lower limb.
Okay, sir. Okay.
Okay, all right, beta. So any doubts in the back angle now? Great, beta. Very good. So I'm closing down the presentation. Okay, so with this beta, we have covered the site solving methods. So practice these site solving methods and cover all of them, all these 5 methods. Be confident in solving these questions. Now, next class when we meet, I will be taking you to plotting of sites. That is the next topic which is lined up. We will be going into plotting of sites. It is also known as staggered observations or simultaneous observations. It is also called as graphical combination of sites. So we will cover some basics first and then we will move on to some solved examples. We will do some actual plotting exercises. So that will clear the concept. So till now what we have done basically covers question number 5. And once we do plotting, it will cover question number 5 and 6. So both these questions will be covered up. And once I cover the plotting basics with you, then I will be sending you one assignment which will cover both these questions 5 and 6. Right, beta?
Yes, sir. Sir, how do you remember all these formulas? We have seen for 4 5 methods, the lab by meridian, all these formulas, C30, M30.
Beta, I'll tell you one thing. When you were in plus and plus 1 and plus 2, how many formulas did you remember?
Yes, sir. But
Hundreds.
we have chart work also.
Okay. I will tell you in total navigation. You combine celestial navigation and chart work both. You won't have more than 10 formulas, beta. So we do not have so many formulas that can be counted on fingers. So no more than 10 formulas. So just write them on a piece of paper. Keep that piece of paper in your pocket. And जब भी आपका pocket में hand जाए, so take out that paper, read those formulas, memorize them. Because forgetting these formulas is a sure shot recipe to disaster.
Ji, sir. Ji, sir.
Okay. So remember them, beta. No shortcut. And I will give you minimum formulas. Okay. Till
Okay.
now, if you remember, तो मैंने आपको क्या formulas दिए हैं? I have given you cosine formula, then Napier rule, amplitude, azimuth. Okay. These 4, they were the basic ones. Then I gave you long bichrone, intercept, x meridian. Okay. That's it.
Parallel
So
sailing.
only
और भी है सर,
हाँ,
और भी है सर.
और कौन से बेटा बताओ?
पैरेलल एंड प्लेन सेलिंग,
In
मर्केटर सेलिंग.
अरे वो तो ट्रिग्नोमेट्री है, साइन थीटा, कॉस थीटा, tan theta. You call them formula. That is trigonometry. Some people have curly brown hair till painted black. All plain sailing, Mercator sailing finished.
Okay, sir.
Okay, all right.
सर वो टीटीटी के सर
Okay, TTT is beta true tiny two words. If the true zenith distance is tiny, means smaller, the intercept will be 2 words. Okay. Now you want to understand the concept. Why is it so?
तो लास्ट में तो मैं समझ नहीं पाया था टीटीटी कैसे, दैट्स व्हाई.
Okay, now is clear how to apply
Yes,
the
sir.
TTT?
Yes, sir.
Okay, so remember only this much. If the true zenith distance is tiny, intercept will be 2 words. And if the true zenith distance is not tiny, then the intercept will not be 2 words, then it will be away.
Okay, sir.
Okay.
Yes, sir. Thank you.
Okay, all right, beta.
So
और
in
बताओ
question,
बेटा.
in question 5 and 6, this graph plotting, we will get simultaneous or staggered both, sir.
You will get one of them, beta. Most of the time in phase 1, you will get a staggered plot. Simultaneous plots are very simple, so usually do not come in phase 1. But yes, they can come. They are easier than staggered.
Okay, sir. Okay, sir. We'll be doing also this graphical plotting now, sir, in this class.
Not today. I don't want to touch it today because clearing up the basics will take 15-20 minutes. Then after that, we will have to break off. So we will keep it for the next class.
Yes, sir.
And Start with basics and then start our practice.
Okay, sir.
Excuse me, sir.
Go ahead, beta.
Sir, I have a doubt on a polar triangle, sir.
Go ahead.
So there are three angles that we are getting, like P and A and B. These angles we are getting. So we confirm it is a polar triangle. And when we go for polar triangle, for the side of P, A, and B, we will do 180-degree minus the angle. So we'll get the polar triangle sides. And then
That's
we
right.
use the cosine formula. And then we find this P dash, A dash, and on the sides of
P
the polar
dash.
triangle. And again, we have to do 180-degree minus to get the primitive triangle sides.
That's right, beta. From the angles of the primitive triangle, you get the sides of the polar triangle. They are supplements of each other. When you get the sides of the polar triangle, you apply the cosine formula and find out the three angles of the polar triangle. Angle P dash, angle A dash, angle B dash. And once you get these three angles, get their supplements. These will be the sides of the primitive triangles.
Okay, sir. They are given like two courses, uh, like on the initial course and the final course in degrees. I'm
Mhm.
struggling in converting that into angles, sir.
Okay, beta. You have the courses now in front of you?
Yes, the initial course is 319 degrees, 22.8 minutes through.
Okay, just a minute. Okay, tell me the initial course, beta. 319.
319 degree, 22.8.
Okay. Final
And then
course?
final course is 298, 49.7.
298. Very good, beta. So these are the courses. Initial course and final course.
Yes,
Now
sir. And
hemisphere, any idea?
yes,
Hemisphere,
sir.
which
They
hemisphere?
are given northern hemisphere, and
North
angle
hemisphere.
P is 33.49.
Angle P is also given. Okay, beta. 33.49. Okay, all right. 33 degrees. Now you see, beta, these courses 319 and 298. Both these courses are in the northwest direction. Agree?
Yes, sir.
Okay. So that means the vessel is moving on a northwesterly track. So let us make a track in the northwesterly direction. Like this. I have made this track, which is going in the northwesterly direction. Let's make a pole somewhere here. We have made the pole. And let's now make the point A and point B. So let's assume this is A. And let's assume that this is B. Correct, beta? Up to here, okay?
Yes, sir. Right.
Okay. Now angle P is already given to us. This is 33 degrees, so we can mark it here, 33. This angle is known. Now the first course is 319. So let me make a rough diagram of the ship. At the initial position, the ship will be going like this. And at the final position, let's make the ship. It will be going like this. Now our course is starting from north, going clockwise, going up to the ship's head.
41, sir.
Okay. So this angle is given as 319. Starting from north, going clockwise, going up to the ship's head. This is 319. Can you tell me what will be angle A?
360 minus angle.
Very good,
41.
beta.
40
So
degree.
41.
40 degree, 37.2.
Very good. So I've just rounded off 2 degrees. No issues. So let us see the final course now. Final course is given as 298. Starting from north, going clockwise, going up to the ship's head. Okay. This is 298. Now, can you tell me what will be the inner angle B?
This is where I'm getting stuck, sir. This final course.
Okay, pay attention. I'll show you now.
Yes,
From
sir.
the bow of the ship to the stern of the ship, beta. What angle will this be?
180.
Has to be 180. Okay. So 180 plus angle B is 298. So 298 minus 180 gives you, so this is basically 118 degrees. This is 118, and 118 plus 180 gives you 298, which is the total green color angle.
Yes, sir. Copy. This diagram is very important. I put like A from A to B, it's going down in northwestern quadrant.
Okay, you made it down like this?
Yes, sir. Like B, where B is, I put A, and where your end of this red line, I put B. I made the diagram like this.
Okay. You
So I
have
thought,
you have to get a hint from the course. It was 298. So you see this is 270. 298
yes, sir,
has to
yes.
be in a upward trend.
So can you tell me one more time, sir? Because I'm thinking as plus 180.
So you have doubt in the final course. Beta, tell me at point B, what is this green color angle? Starting from north, going clockwise, going up to the ship's head.
That is the true course.
That is the true course, na?
Yes, sir.
So that is given as 298, right?
Yes, sir.
So green color angle is 298, correct?
Yes, sir.
Now this green color angle is equal to yellow angle plus red angle, right?
Yes, sir.
So this red color angle is from the bow of the ship to the stern of the ship. So it has to be how much?
180.
From the bow to the stern, it has to be 180. So 180 plus angle B, the yellow angle is the B angle, should be total 298. Correct, beta?
Yes, sir. Yes, sir.
Okay, so B has to be 298 minus 180, which is 118.
Understood, sir.
Clear, beta?
Yes, sir.
Okay, good. Okay, so closing this down now. Great,
sir,
beta. Go ahead.
one more. There is one question. Rumbline distance between two places in latitude 47 degree north is 1132 nautical miles. What is the shortest distance between them?
Okay. Let's go to the whiteboard. Let's see, beta. Give me a minute. I'll put the whiteboard. Okay, let's erase this. So it says the rumbline distance between two places on the same latitude is how much?
1132 nautical mile.
1132. What is the shortest distance between them?
Yes, sir.
That's it? No, nothing else is given?
Yes, sir. That's it. That's it.
Okay, all right. So let's make the triangle. Both these are at the same parallel of latitude. So let's make a rumbline track also, and let's make a GC track also. Okay, let's call this as A. Let's call this as B. Let's assume vessel is moving like this. Both of them are on the same latitude. Now the rumbline distance between them is 1132. Both of them are on the same parallel of latitude. So this has to be the departure, right, beta?
Yes, sir.
This has to be the departure. So the departure between A and B is 1132. बेटा और कुछ भी नहीं दिया है यहाँ पे?
No, sir.
Latitude or something, nothing is given.
latitude is 47 degree north.
Ah, right. That was the missing part, na? 47 degrees is the latitude, na?
Yes.
Okay. Now, beta, you have the departure, right? You have the latitude. Can you find the D long?
Yeah, by the plane sailing, we can use this and then.
Yeah, use parallel sailing, beta. Departure is equal to D long into cos of m lat. So, or you can say departure upon cos of m lat, which will be in this case cos of 47 will give you D long. Right?
Yes, sir.
So just tell me, punch in these numbers in the calculator. 1132 divided by cos 47. How much is the D long?
1659.8.
Very good. 1659. And convert it into degrees and minutes, beta. This is the D long.
27 degrees, 39.8.
Very good. 27 degrees, 39.8. So this is the D long between these two places. Right? So now you get the D long. This angle P, which is the D long, is 27 degrees, 39.8. Now the question becomes very simple. You have angle P also, you have side PA also, you have side PB also. Apply the cosine formula, get AB, great circle distance, and the question is solved.
Yeah, okay, sir. Thank you, sir.
Clear? Okay. Very good, beta. Great. So let's close out for today. And next class, we will start with plotting. Right, beta?
Okay, sir.
Okay, dear. See you in the next
Thank
class.
you,
Bye
sir.
bye. Bye bye.
Good evening,
Thanks,
sir.
beta.
Thank you.
Bye bye.
Thank you, sir.
Thank you,
you,
sir.
Bye bye. Thanks. Thanks.
Thank you, sir. Thank you. Thank you.
Okay, beta. Thanks. Welcome. Bye bye.